for this problem it says the cylinder x squared plus y squared equals 1 intersects the plane x plus z equals 1 in an ellipse. Find a point on this ellipse farthest from the origin. So here we have two equations given, and we're supposed to find where on this ellipse of intersection that is farthest from the origin. So here, farthest from the origin means we are trying to maximize the distance, right? So we're maximizing some kind of distance here. All right, so first of all, so that means our main equation is going to be the distance formula, right? And from the origin means minus 0, 0, 0, right? The point 0, 0, 0. And then remember, maximizing distance is the same thing as maximizing the square of the distance. Okay, so our new f of x, y, z is going to be x squared plus y squared plus z squared, and that's just to make our lives easier. Okay, and so this is our main function, right? And now let's get the other ones in the proper form as well. So the first one, this top one here, we can actually write as x squared plus y squared minus 1 equals 0. And we'll make this one be our g of x, y, z. Okay, so that's equal to x squared plus y squared minus 1. And the other one we can rewrite as x plus z minus 1 equals 0. And I'll make this one be h of x, y, z. So that's going to be x plus z minus 1. Okay, so here we have our two constraint curves, all right? So that means, and we have our main function. So we're going to set up the following equation on the next slide. But we'll have the gradient of f is equal to, or at some point, is equal to lambda times the gradient of g at some point, plus, and this symbol is called mu. It's like a fancy U sort of thing. And that's another Greek letter. And then times the gradient of h at that same point. Okay, so this is our like expanded Lagrange equation, right? With an added constraint here. Okay, so in order to set up that Lagrange equation, we have to figure out what are the gradients of all of these functions. So first of all, let me rewrite those. So f of x, y, z is equal to x squared plus y squared plus z squared. Okay, and then g of x, y, z is going to be x squared plus y squared minus 1. And finally, our h of x, y, z is equal to x plus z minus 1. Okay, so first of all, let's find gradient of f. That's simply going to be a 2x, a 2y, and a 2z. Okay, let's see, the gradient of g is a 2x, a 2y, and a 0. Okay, and then the gradient of h, that's going to be a 1, a 0, and a 1. Okay? Alright, so now we can set up our equation, and then we'll go from there. So we have a 2x, 2y, and a 2z on the left-hand side there. And then we have lambda times gradient of g, which is 2x, 2y, and 0. Then we have that added to mu times 1, 0, 1, okay, which was the gradient of h. Alright, so now we have our equations. Now let's kind of simplify the right side to make it look a little nicer. So on the left side, we still have that 2x, 2y, and 2z. And on the right side, we have 2x times lambda plus a 1 times mu, comma, 2y times lambda plus 0 mu. Okay, and then the last one is 0 lambda plus 1 mu. Okay, so now we can set up our mini equations by setting the components equal to each other. So our first one's going to be 2x should be equal to 2x times lambda plus mu. The next one is going to be 2y is equal to 2y times lambda, because the 0 goes away, right? And then the third equation is going to be 2z is equal to mu. Okay, so I'll rewrite these on the next slide. So we have a 2x should be equal to 2x times lambda plus a mu. 2y is equal to 2y times lambda. And 2z is equal to mu. Okay, so for this equation to be true, let's look at this one first of all. So if you divide by 2y, we just get that lambda equals 1, right? So that could be an option, or these could be equal if y is equal to 0, right? So, or y could be equal to 0. So we have these two options here. So this is option 1, and this is option 2. So let's explore what happens when we pursue option 1. All right, so option 1, we're going to say lambda is equal to 1. Alright, so here are our equations again. 2x is equal to 2x times that lambda plus mu. And then we have our 2y is equal to 2y times lambda. And then we have 2z is equal to mu. So if we plug in a 1 for lambda, so this one works out, right? So this guy works out, that's good. Lambda is equal to 1, great. And then we have, if we plug in a 1 here, we get 2x is equal to 2x times 1 in for the lambda. We have our mu just sitting there. So then we have a 2x on this side, on the left, and a 2x on the right side. So if we subtract that over, subtract, we get that mu is equal to 0, okay? So then what we get is that, so if mu equals 0 here, then we can plug that into the right equation. So we have 2z is equal to 0 in for the mu, and then therefore z is equal to 0. So here we solve for one of the variables. So when z equals 0, then we can go back and use our original constraint equations, right? So our x squared plus y squared is equal to 1, and our x plus z is equal to 1. Okay, so here we can plug in 0 for the z spot. So we have x plus 0 is equal to 1, therefore x is equal to 1. Okay, and now we can use that as well in for this equation. So we're going to plug in a 1 for the x spot, and we'll solve for our y. Alright, so we get 1 plus y squared equals 1. So y squared is going to turn out to be 0, so y is equal to 0. Okay, so here we just solved for a point, or yes, a point. So 1, 0, 0 is a solution, okay? Or should I say a possible solution, right? Because remember, this was only when we tried lambda is equal to 1. Our other option was for our, for our y to be equal to 0, remember? So we'll try that one, the second method on the next turn. Okay, so here's the second approach, right? So we have the y could just be equal to 0, okay? So if we start with that, then we'll write down our mini equations again. So we have 2x equals 2x lambda plus a mu, and then 2y is equal to 2y lambda, and then we have our 2z is equal to mu. Okay, so if we make our y equal 0, then that means y is equal to 0. Okay, that fulfills that equation there. And then we can basically just kind of plug it in. So we're going to use our constraint equations again. So we have our x squared plus y squared is equal to 1. So let's plug it into this one actually. So we're going to plug in a 0 for y. So we get x squared plus 0 squared is equal to 1. Therefore, x is equal to plus or minus 1. So here again, we kind of have two branches, right? Two roads to follow. So the first one, let's do x is equal to a positive 1, okay? So now, if we say x is equal to positive 1, so here's our first branch, and here's our second one, so x is negative 1. So now we're going to make use of the other constraint equation, okay? And we're going to solve for the rest of the variables. So here's our constraint equation. If we plug in a 1 for x, we get 1 equals z, 1 plus z is equal to 1, okay? And therefore, z is 0, all right? And then again, this was all of this branched from y equals 0. So we have x equals 1 for this one, y equals 0, and z equals 0. So this is just our 1, 0, 0, which we already found when we set lambda equal to 1. So that one's just a repeat one. We don't need to worry about that at all. Okay, so 1, 0, 0, we already have that in the bank kind of thing. Okay, so now let's look at x equals negative 1, all right? So let's plug that guy into our constraint equation. So x plus z is equal to 1. If x is negative 1, then we have that z is going to turn out to be a positive 2, okay? So now we have the set of x is negative 1, y is 0, and z is a positive 2. So now we have the point negative 1, 0, and 2, okay? So this is a new one, so we can keep this one. All right, so now let's write what we've learned so far. So we've said that if the first method, right? So if lambda equals 1, which satisfied that middle equation, then we got the point 1, 0, 0, okay? And if we set y equal to 0 in order to satisfy that middle equation, we got negative 1, 0, and 2. So now we have a dilemma, right? This is kind of like, so we have two candidate points, but we don't know which one is going to maximize our main function, right? Our distance. So let's just see. So our function, our f of x, y, z, the one that we want to maximize is the distance, right? We want the farthest distance from the origin. So again, that equation is x squared plus y squared plus z squared. So if we just plug in these points, we can see which one is goes the furthest. Okay. So here we're plugging in the 1, 0, 0 first. So this is just going to turn out to be a 1. And then if we try plugging in the second point, we have -1, 0, and 2. That will give us a -1 squared plus 0 squared plus a 2 squared. So that would be 1 squared plus 4. So that's going to be a 5, which is the larger answer. Therefore, this one must be the final answer. This is the point at which the distance from the origin is maximized, given our two constraint equations. Okay? So that is all for our practice problems video on the Lagrange multipliers, or optimization in several variables with a constraint, right? Okay, so that does it. I hope that helps, and happy studying.
Do